Hello, everyone, and welcome to this week's Believe in Serverless live stream. Actually, the first one we're doing in a more EMEA-friendly time zone. So if you're in EMEA eating your lunch, welcome. If you're in America and you're up really early, particularly a big thank you for actually getting out of bed early to do this. I'm super excited, actually, for this week's guest, who I will introduce in just a second. Before I do that, a really quick shout out for some of the other events we have coming up on Believe in Serverless. So later on today, Andres is going to be building a game show front end or something like that with Memento Topics and AWS. So that'd be super cool. And then next week on Tuesday at 4 p.m. BST, and I'm not going to do the time zone maths live on air. We have Luca Mezzalira. I'm sure many of you know Luca. He's going to be talking about Lambda performance tuning with Node.js, which is a really fantastic segue, actually, to this week's guest and Lambda performance tuning. So super excited to have Richard Davison here. Richard, do you want to just do a quick intro first, or are you going to do that as part of the actual content?
No, I think it could be good to have just a short intro. So, hi everyone, thanks for tuning in. If you're here, or if it's just me and you, James, we're happy to talk with you as well. My name is Richard Davison. I work as a solution architect, focusing on application modernization, and that means I mainly help our partners and customers at AWS make the best out of our services from an app modernization perspective. That particularly means working with container and serverless services. So yeah, I'm super excited. Can we maybe bring up the screen share? Yes, here we are. So what I will talk about today is something I've been building on for quite some time now. I think it's close to a little over 1.5 years. And this is LLRT for AWS Lambda. So LLRT is short for Low Latency Runtime. And it's a custom JavaScript runtime built from the ground up to address the growing demand for fast and efficient serverless applications. And I wanted to start by addressing this, what I mean by built from the ground up, and give some sort of rationale why I think this is needed and what kind of led up to this project. So in its current state, Lambda is very successful in supporting a whole heap of different programming languages and frameworks, everything from Java to Node to Python, etc. But to be frank, most of these languages and supported in Lambda by default are built for general purpose execution. And they often have a bit of legacy, meaning that they were created a while ago. I think Java somewhere in the 90s. I don't know when Python was out, but it's been out for a very long time. Even Node has a few years on its neck now. And if you exclude custom runtimes that you can build with Lambda in Rust or C++ or Go, these languages were not really designed for short-lived runtime instances, or that is often characterized by serverless compute, right? And the languages that Lambda support out of the box, in their design traits, they often are better for longer running tasks. Many of them contain technologies that make them actually more optimized the longer they are running. So rather than building on top of the existing solutions, I challenged this model and I wanted to try to design something from scratch, adhering to 3 fundamental principles that are very desirable in a serverless ephemeral environment. And these 3 traits that I wanted to design for was startup time, performance, and efficiency. So I wanted to build something that initialized quickly to reduce the so-called, the infamous cold starts that everyone hates. But they're actually not that prominent. We'll talk about that in a second as well. And I want to have something that is really performant, so they can provide a rapid compute layer. And I also want to build something that is very efficient and consumes minimal resources, because resources in Lambda are directly related to cost. So the less resources and the faster we can make things, the lower the cost, which also improves the user experience. And you may wonder, where does JavaScript fit into this picture? So what I've done is to build a new custom JavaScript runtime from scratch that is tailored for these principles that I mentioned here before. So why JavaScript? So first of all, JavaScript is one of the most popular ways of executing Lambda functions, and they're actually one of the most popular ways of building serverless apps in general. As you know, it offers full stack consistency, so your backend and your front-end application can share some common code. And using a unified language for different parts of your stack can be an additional benefit as well. Another benefit with JavaScript is that it offers a very rich package ecosystem and a maturity with a large community that can help accelerating development for your application in general. And it's often recognized as its user-friendly nature, making it easy to learn, to read, and to write. And what's even better with JavaScript is that it's actually an open standard known as ECMAScript, which has been implemented by different engines. This means that I can build upon a solid foundation by using a lightweight engine that are adhering to my 3 principles of startup time, performance, and efficiency. There is a specific engine that kind of ticks all of these 3 boxes that are my desirable traits, and it's called QuickJS. And QuickJS is a super small JavaScript engine. It's less than 1 megabyte, and it also supports the most recent ECMA specification, that is the JavaScript specification, ES 2023. It's written in C, which means that it's also very quick and starts in just a few milliseconds. But an engine is not a runtime. So a JavaScript engine can only execute JavaScript, but it has no APIs to communicate with external resources, such as the network, the file system, input and output, and similar capabilities. So we need a way to add them. Otherwise, we can't do much with an engine. Similar to a car, it's not very useful if the car only consisted of an engine. We need all the other components as well. And we want these APIs to not regress on startup time or on sacrifice on performance or on efficiency. So we could do it in C, but nobody really wants to build in C. It's very error prone, very risky. You will mess up, definitely. So there has to be a better way. So let's use Rust. So if you think about it in its essence, and it's quite simplified, LLRT is basically QuickJS plus Rust. If you combine those two, you get LLRT engine. And all of the APIs that I have built in Rust follows the same specification that Node has. And this comes with a couple of benefits. The first one is that you would know how to use them, because you might be familiar with how Node are implementing, for instance, file system communication and network communication as well. It also means that if you run into an API, or if you try to use an API in LLRT that is not supported or is not implemented yet, you can switch back to Node and you don't have to change your code. So no effort has been wasted, and you can simply move back and switch between the two. It's important, however, to note that all APIs that LLRT has implemented are Node compatible, but not the other way around, right? So there are obviously APIs in Node that is not implemented in LLRT, but LLRT follows the Node specification. So a couple of feature highlights. LLRT, again, is built from the ground up in Rust, which means that it has pretty much negligible cold starts. So cold start duration is less than 100 milliseconds for a whole heap of use cases. So even for communicating with AWS SDK, we have greater than 10x performance versus Node.js. It uses not the latest JavaScript specification, but almost the latest, ES 2020, with many Node.js APIs that are supported. And we want it to be a sort of a low effort migration from Node.js. Obviously, this depends on what APIs you're using, but for simpler Lambda functions where you have a lot of integration code, it's quite simple to migrate to LLRT or support LLRT. It comes with batteries included. So the LLRT binary and executable comes bundled with the most popular AWS V3 SDKs for JavaScript. It also comes with cost and performance benefits. So more stable performance leads to more than 2x lower warm starts in addition to those 10x faster cold starts that we saw. And I think it's enough talking. Let's show its capabilities in a demo, and we will discuss the traits of LLRT and how it can be so fast while we continue the presentation. All right. I hope the demo gods are with me. So I'm bringing up. Here we go. Is that visible, James? Do you see it? Yeah, I hope this is visible. So we are now inside of the AWS console. I have created a simple Lambda function here that takes some event here and puts the data together with a randomized ID in a stringified format on DynamoDB. So I'm first creating the DynamoDB client and then the document client for simpler serialization. And I'm importing them from AWS SDK, client DynamoDB, and libDynamoDB as well. I then return a simple status code of 200. Okay. So let's now first test this with the regular Node.js Lambda function. So I'm going to select here in runtime settings Node.js 20. And I'm using an ARM architecture. So let's go to the test tab. I'm executing this with a very simple JSON payload. And this will be a cold start since I changed the runtime settings from custom runtime to Node. So this is with Node. Let's execute. And we saw now that we had an init duration of 360 milliseconds and a duration of 984 milliseconds. So about 1.2 seconds for this particular compute to run. Because when you're using a provided runtimes, you have to combine these two values to get the total time. So init plus duration. And I have configured this Lambda function to use 128 megabytes of allocated memory, which means that it will have a pretty weak CPU resources as well. So about 1.2 seconds. I also consumed, while running this here, 89 megabytes of those 128. That is the max memory being used. So what I'm going to do now is go back to the code. And do note here that I have added a file called Bootstrap, and this is actually the LLRT binary. So if I'm downloading it from GitHub, it will be in a zip package with this binary already included. So this Bootstrap here is the LLRT executable. So what I simply can do now is to go into runtime settings. I'm going to switch from Node.js 20 to Amazon Linux 2023 OS only runtime. And hit save. Right, I'm going to keep the code exactly as it is. I don't make any changes here. And I go back to the test tab. And this will also, again, be a cold start. And you saw that that was almost instant. We now, instead of 1,200 milliseconds in total, we have an init duration of 40 milliseconds. And we have a duration of 24. So in total, we have a build duration of 66 milliseconds versus 1,200 something. And while doing so, we only consumed 22 megabytes of memory. So this means that we have practically 1,200 versus divided by 66. We have more than 18 times improvement of cold starts. And we didn't touch the code at all. So it's performing the exact same task. It's storing the exact same data on DynamoDB. And we can do it almost 20 times faster, which also means that I have a significant cost saving as well. And do note, this is not only for cold starts. So if we run it again here, we can see 29 for a warm start. We continue 8, 20, 16, 8, 19, 11, etc. You see here, it's consistently below 20 something milliseconds, right? Often Sorry about that. Often way more than that, or way lower than that. And as you can see, also it's very consistent in its performance characteristic. It stays in about 10 milliseconds from one invoke to another at warm starts. If I compare this with going back to Node.js, we will see a different characteristic in its runtime performance. So I have now updated the runtime to Node.js again, and I'm hitting the test button. You can see again, we are at this way over 1 second, 1.2 seconds almost of execution. And if I'm testing again to simulate a warm invoke, we can see that rather than something like 30 or 40 milliseconds, or even 8 or less than 20, I get 300. Second one will be better, or the third one will be better. As we can see, it goes down, but it also goes up. It's a bit inconsistent. Now I got 100, 50, 52, 57, 20. 20 is something like we get from LLRT. But you can see it's very fluctuating. And we will talk about why this is. But you can also maybe see a pattern here that even for warm start, we will have a significant better user experience and a lower cost, as well as a better performance footprint when running LLRT. So let's go back to the presentation. This demo is a very typical use case when building Lambda function that you communicate with AWS SDK. We will see the similar performance benefit when running other SDKs, not just DynamoDB. And you don't only have to use DynamoDB, of course. You can do other things as well. And we will also discuss a few use cases now. So when is this good to use? This is good to use for latency critical applications. It's also good to use with functions that have extremely high volume that sit in front of everything else, or for instance, a Lambda authorizer, typical use case. It can be good for data transformation when you're doing some ingestion or consolidation of data and storing it something else. Maybe you're reacting to some sort of event from EventBridge and you want to put something on S3, or you want some very lightweight data manipulation and you want to have it with low latency. It's also good, of course, for AWS service integration, communicating with downstream AWS services. Or you can even do server-side rendered React applications, which also might sound like it's complicated, but it's also something that LLRT handles very well since its performance characteristics. And how can it be so fast? What makes this like almost 20 times faster for cold start that we saw, and more than 2x faster for warm start versus Node.js? So there are a couple of things that is the main reason behind this. So if we take a step back and try to, in general, get a perception of like how can I make any code run fast on Lambda, or any application run fast on Lambda? So there are like 4 major things that you can do. If we exclude like the obvious one, like configuring Lambda with more memory. So say you would want to have as low cost as possible. So naturally you pick with 128 megabytes of allocated memory, which means that you will have the weakest CPU resources as well. So how can I then make it fast? So I have to make my Lambda function light, because the weight of the Lambda function or the package size that you deploy has a direct implication, or directly affects your cold starts, because the code that Lambda pulls in and loads into the worker needs to be stored somewhere. It's actually stored in S3, and it's pulled in from S3. It's downloaded to the worker, and then it's loaded into the Firecracker virtual machine, and then it's executed, in this case, by Node or by LLRT. So I have to make it light. And there is actually kind of a misconception here that package size doesn't affect Lambda functions. It actually does. And there is a bit of nuance here as well, that sometimes you don't always see this delay because it's not measured. The download time from S3 is not measured in the execution duration, but you will definitely notice it when you do end-to-end testing. And it's also a bit complicated because it depends where the code resides when you actually when actual cold starts occur. So it can be downloaded at the worker, which means that the cold start will be faster. But in worst case, it would have to be fetched from S3, which will make the cold start longer. So there's a difference between a cold start and a cold start, and I just want to make that clear. But nevertheless, we should focus on making our code and package artifact as lightweight as possible. And there's also a bit of a nuance here as well between how you package your Lambda functions. There is OCI package format, that is container package format, and it has a different packaging mechanism, which in that case, it's not as sensitive to keep it as lightweight. But in general, to have the most performant Lambda function, we should keep it as lightweight as possible. And if you need more than, say, 30 megabytes, it's better to ship it as an OCI, as an open container image format, because that will have better performance versus a zip deployment package. Another way to make code run fast and my application run fast is to utilize parallelization inside of my code. So doing multiple things at the same time that are not dependent on each other. It might sound trivial, but it's actually something that we see many times being overlooked. Can you pull in something from multiple resources at the same time? You should do it. It's very likely that your Lambda function spends a lot of time idling or waiting for downstream dependencies, such as a database or some HTTP service. So doing things in parallel will definitely not only speed up cold starts, but also warm starts. You should also consider making as much code as possible native or using a compiled language. Rust is a good example. Others is C, C++, or even C or Go. Also good candidates for running really, really efficient Lambda functions. And of course, not everybody can code or want to code in natively compiled systems level programming languages, right? And this is also one of the reasons why LLRT makes this a bit more applicable for a general audience, where you have maybe a JavaScript workload that you still want to have similar performance to native. And the last one I want to address here is also that it's very important to keep the code running eagerly evaluated. In a traditional serverful environment, it's actually better to have something lazily evaluated, meaning that you only execute the compute when it's actually needed. But in Lambda, when there's a cold start, the actual execution environment, which loads your artifact for the first time, during the cold start, it gets a CPU boost. So you would have more CPU during the initialization of your Lambda function. This means that adding code or running code outside of your handler, where you don't have access to the event, will be beneficial from a performance perspective, because you have quite frankly more CPUs. And this means like doing as much as possible. What can you do? You can initialize HTTP connections. You can pre-compute or build sort of lookup tables or anything that you can't do at compile time, but it's still necessary to do at runtime. You can do that. You can also initialize database connections and then use them inside of your handler. This will save you possibly hundreds of milliseconds, a bit depending on what runtime you're using. But it's a very, very good tip for performance increase. But then, how can LLRT be so fast? So what is the secret behind its performance that we saw? So first of all, QuickJS, again, simpler engine versus Node. And Node is an extremely sophisticated project. So LLRT is not meant to compete with Node, but rather to complement Node. Similar with Dino or Bun, they're also very sophisticated, but they're general purpose. They're not purposely built for serverless execution environments, but they're also very capable. So they will have way more APIs than LLRT, but as a trade-off, it might not be as efficient running on serverless environments. So the simplest way of increasing performance is doing less things. And since LLRT is a lighter engine and also a lighter API, it's naturally faster just by not doing as much, simply. The second one is there's a lot of optimizations that I've specifically added for the AWS SDK v3. Again, AWS SDK is a general purpose. The SDK doesn't know where it's being executed, but now I know, since I'm building the runtime and I'm embedding the SDK, I can do specific optimizations for the SDK that have performance benefits on serverless. And one of the biggest contributors to performance is that I have shifted a lot of complexity from JavaScript to Rust, meaning that a lot of APIs have been implemented in Rust rather than in JavaScript, so they will have an instant performance boost. And the last one is it's lightweight. So the whole runtime in itself comes in just under 3 megabytes, and that is including the AWS SDK. Let's now take a bit of a deep dive on these different components and see how they contribute to fast performance and low cold starts. So QuickJS, it's 55,000 lines of C. So it's kind of a single C file containing the whole engine in itself. So it's less than 1 megabyte. So the engine itself is less than 1 megabyte. If you compare that with something like V8, that is the JavaScript engine in Node, it's something, I think it's around 20 or even more, 20, maybe 40 megabytes. So it's, way lighter. It's written by Fabrice Bellard. It's an extremely talented programmer, the mind behind QEMU and FFmpeg that you may have heard of. It also offers extremely fast startup since it's written in C and tailored for fast startup. It's naturally so as well. And it has zero dependencies, so it doesn't depend on anything else, meaning that the engine itself can focus on just being as fast as possible. And it has ES 2020 support, actually has ES 2023 support recently, but in LLRT we only have ES 2020, but ES 2023 is coming. And it also has no just-in-time compiler. And a just-in-time compiler is something that exists in almost every other JavaScript runtime. And it's a very sophisticated technological component that is great for longer running applications. So what a just-in-time compiler does is that it actually analyzes your JavaScript code and converts it into native machine code. So it actually compiles JavaScript on the fly in order to make it run more efficient. The problem with this, though, is that it takes compute in order to do the compilation. And it doesn't really matter when you're running a serverful environment or running a traditional web server, because this might only happen once or a couple of times, and then we get the instant performance benefit. But in Lambda, we have very limited resources. So we want to conserve the CPU and memory resources that we have to do execution instead of compilation. This is also why you saw in the demo that the Node.js example, the execution times went very much, up and down. They were very fluctuating. They didn't have a stable performance characteristic. And this is due to the just-in-time compiler. With the low memory that we have, the just-in-time compiler has to evict certain code from its compile cache. So this means that code might get what's called decompiled and then have to be recompiled. A just-in-time compiler also have to make assumptions on how the code is being used. Since JavaScript is a dynamically typed language, it has to look at the type and say, okay, now this parameter here is a string. Let's assume it's a string. I'm doing optimizations based on that assumption, but that might change. We might get a number the next time, or we might hit a branch, like an if statement, which didn't occur on the first compilation, etc. So statically analyzing and trying to find optimal performance and bytecode generation, or machine code generation rather, for a just-in-time compiler is very complicated. That's why it requires some time in order for it to be efficient. And the engines used in Deno and Node, V8, or in Bun, JavaScript core, they are all built for assuming that a JavaScript just-in-time compiler is in place. So they kind of built around that. You have the option to disable it, but it was designed assuming, or designed for an environment where a just-in-time compiler is critical, right? So it wasn't designed to run without a just-in-time compiler and straight off the interpreter. Finally, or not finally, but next we have the JavaScript SDK v3 optimizations that I have applied. So, like I mentioned before, all JavaScript methods that I can have been replaced with native Rust methods. This means things like hashing, XML parsing, network calls, etc., are all happening in Rust. And the code in JavaScript that you execute is simply communicating with this Rust layer. We also try to limit the number of objects that are created. Object creation in JavaScript can be expensive, especially if you have no just-in-time compiler. So objects are not created as extensively. This means that we cache endpoints. So there's a quite sophisticated endpoint lookup based on your configuration on what endpoint that you should reside to. This is being cached inside of the LLRT runtime. And we do eager connections to the SDK endpoints. So when you actually import an SDK client inside of JavaScript, we already at that import level initialize the connection. So as soon as you import it, you will have a connection being initialized, which means that you will automatically save on connection time. Because remember, eager initialization that we talked about before, it is a performance benefit of initializing connections eagerly, and LLRT does this for you. And they also happen in parallel. And then they are simply awaited before your code runs in the handler. And we also have minified, bundled, and code splitted the entire SDK. So parts of the SDK are reused, and they are minified and bundled to reduce the code size of the SDK. And finally, it's converted into QuickJS bytecode. That means that I can avoid a parsing phase. So when you execute JavaScript in QuickJS, it's first lexed and parsed, meaning that there's like an abstract syntax tree or an AST being built up, and the source code is parsed, and it's compiled, or it's not compiled, but it's then transpiled into an internal representation, that is the QuickJS bytecode, that is then executed. So I can avoid the two first steps by doing this at compile time, converting the JavaScript SDK to JS bytecode. And to further reduce the size of the JavaScript, we apply compression on the bytecode. So bytecode is aggressively compressed with Z standard at the highest compressing settings. So Z standard is a compression algorithm used by Facebook, and it's actually invented and created by Facebook. So this will make the already minified JavaScript code shrink from about 2.3 megabytes to 543 kilobytes. So it's a massive reduction in size. And the compressed bytecode is then actually embedded inside of the executable itself. So there's no additional file reads. It's simply inside the file that you're running, inside of that bootstrap file that we saw before. And it's stored in a perfect hash function, so or a perfect hash table. So the hash keys and everything for lookups, like when you do an import and provide a name, that name is actually has a pre-calculated hash, so meaning that the lookup will be extremely fast. That doesn't have a major performance impact, since I don't have like a million packages to import, but it still has some additional benefits. And you might wonder now, okay, but if you compress, that takes CPU. Wouldn't that like mitigate the whole, cold start time? So the thing with compression here is that Z standard is such an efficient compression algorithm, so it's actually worth compressing and reducing the size of the artifact. That takes actually less time than actually do the decompression. And you're not likely to need all of the supported SDK in your function. You'll only use a part of it. So all of those imports will be decompressed on demand, and this will happen eagerly when we have more CPU. So it doesn't really add any performance penalty, not in a measurable way, anyways. Moving on to some Rust optimizations that we apply. So Rust is compiled with some aggressive optimizations. So we use O3, so the highest or level 3 optimizations in the Rust compiler. This means that things like monomorphization, where it converts generic code into more specific code. It does loop unrolling, etc. Meaning that if you have like a loop and it sees that it will be more performant of like not looping, then it does that. So the compiler is very clever. It will automatically convert like iterators into handwritten code, for instance. You can look this up. It's very sophisticated how it works. And we're also stripping debug symbols to further reduce the size. The Rust executable is also compiled with panic abort, and we're building the standard library as well to further minimize the code size with these aggressive optimizations as well. And you have to use the nightly compiler to do that. SIMD stands for single instruction, multiple data. This means that we're using SIMD instructions where we can. So when you try to do reading data, for instance, it can be an added performance benefit of trying to read multiple data or perform operations on multiple data at the same time. For example, finding a character in a string, you can load a whole heap of characters into memory and then finding the character in like one instruction. You don't have to go through each and every character. So these are especially this is special features built into the CPU, and it's called SIMD. And we're using a library called SIMD-JSON that performs these highly optimized multiple data operations to parse JSON. Similarly, we do that with JSON escaping to escape strings in JSON. We do that with XML parsing, with hashing, the encoding, etc. It's really very performant. It's more performant on larger inputs. That's where you see the biggest benefits. And finally, we also do link time optimizations. So LTO, it's another setting that you can apply when compiling Rust that further optimizes the code at link time, removing unused code and does some more heavy optimizations. We compile Rust and target Muscle. So Muscle is an alternative libc. So the C standard library, C is actually a runtime that comes with the standard library. So this is a like more modern version called Muscle, rather than the GNU C standard library. The benefit of using Muscle is that it's more lightweight, doesn't contain as much legacy. So we can make the whole executable smaller, again, contributing to faster code starts. And we use a custom allocator. So we do memory allocation, for instance, working with strings or dynamic data, vectors or lists. We need allocation, we need to allocate memory and deallocate memory, etc. We use a custom allocator. I think this one is from Microsoft. It's called snmalloc. There's a Rust binding that we can use. snmalloc is a message passing allocator, which makes allocation very fast. It's much faster than the one built into Muscle libc. That it has also a major performance benefit. And moving on, we are, as a final step to reduce the size of the whole executable, we apply something called binary compression. So at compile time, we take the LLRT binary, that is an ELF executable. We then split it into different parts. In this case, we split it into 2 parts, and we actually compress them with sed standard. Remember this real-time compression algorithm that I was talking about before. So we take it, split it apart, compress each part with sed standard, and we then take those parts and embed them into a very, very small C program. And this C program then, when it's running inside of Lambda, will take those parts and in a multi-threaded fashion, decompress those parts into something called a memory file descriptor. So it will do in-memory decompression and then execute that file straight off memory. And this actually saves maybe 10 to 20 milliseconds of execution time, because we can apply a very efficient compression algorithm on the entire binary. So this reduces the size of the binary from around 5-6 megabytes to less than 3. So we have like a 2x reduction in binary size. Again, this decompression adds some time, but it's something like 10 or 20 milliseconds. So it's worth, again here, the CPU benefit is worth over the additional download times. So some considerations and compatibility. What's the catch? You might wonder, why aren't I using, why shouldn't I use LLRT for everything? If I have a JavaScript workload, why don't I use it for everything? There is obviously some trade-offs. As I mentioned before, in order to make it so fast and efficient, I have to make it light. And by design, it's not supporting everything from Node.js. It supports a fraction of the Node.js APIs. We have kind of made a decision not to support everything, and we will never support everything. So it will never be a drop-in replacement for Node.js. And that's, again, by design. The more APIs that we add, it will slightly add to the cold start for every one of those and add to the size of the binary. But with that being said, most things that you actually need are being implemented. Things like doing network calls with the fetch API, doing file system calls with FS promises. We have console encoding. We can call sub-processes. You can even spawn a simple HTTP server if you want to. We support ESM and CS imports transparently, so you can use them however you want, actually in the same file as well. Streams are not supported in a native fashion, but they're supported in the JavaScript fashion. So they might not have the best performance. Everything else you see here is pretty much in Rust. So when should you not use it then, right? You should not use LLRT when you have very compute-heavy JavaScript. So that means when you have JavaScript that is executing a lot of JavaScript in very with loops with millions of iterations or hundreds of thousands of iterations, because this is where the lack of a just-in-time compiler is noticeable. So when you do very, very compute-heavy JavaScript, there is a huge benefit of having a just-in-time compiler, because that compiler can make assumptions on how things are running for every one of those iterations and make it more optimal. And this is not the case in LLRT. But on the other hand, most compute-heavy tasks that you might want to do, for instance, calculating a hash of a certain value, that is all happening already in Rust. So you would have to see how it performs and works for you. Similarly, streaming. If you're streaming data from endpoints, if you're streaming to the file system, etc., that API is very limited right now. We're working on building it in Rust, but the API is very complex. It might take some time, and we might have to make some sacrifices in order to have it implemented reasonably. Simulations also kind of follows the same argument like compute-heavy JavaScript, is that if you run simulations also containing a lot of JavaScript, it might be better to use something like Node. And there might be dependencies that doesn't work. In fact, most dependencies won't work, since they are likely to depend on APIs that we haven't support. And an example of this is some dependencies are using NAPI, so the Node native API. So they are maybe having, you have Node dependencies that are using C++ resources or using compiled resources. Those won't work. And what we recommend here instead is to call what you're trying to do with the child process. So say you're doing video encoding, you can simply spawn a child process calling the FFmpeg binary, and then just work with what you have from the file system, reading in the input files and writing input files, etc. So then how do I actually use it? There are a couple of ways. These are all documented on the GitHub page. So you can, the recommended way right now is to either use it as a layer or ship the executable with your code. This was what we saw in the demo. I just added the LLRT binary there, called it Bootstrap, downloaded it from the GitHub release page. So it's very simple to add. We also have a couple of examples on the repo on how to add it with SAM, how to add it with CDK. There's even a CDK level 3 construct that you can add as well. And there are also examples on how to use it with a SDK that is not being embedded. So not all SDK clients are embedded. So also check the repository for examples where we have an external SDK client. For instance, the EC2 client is not embedded. So we have an example showcasing that. So let's now look at some numbers. We saw some numbers in the demo before, but here's a more of a consolidated view. If you look at the startup time, this is running like a hello world. I think this is a bit, yeah, it's kind of it doesn't tell much to run a hello world, but you can get a sense of the lightness of the application. So let me do the highlighter here. So we can see here, I'm doing exactly the same thing. It just prints hello world to the console. So running this with LLRT, hello, we can see that it takes about, I don't actually see it here, but it takes around 10 milliseconds, something like that. Similar to QuickJS here. Oh, here it is. It actually takes 4 milliseconds. Comparing this with QuickJS, so you can actually use QuickJS as it is. It has no like performance overhead. It's actually slightly faster here. So we can see that it's 8% slower here, running the same thing with QuickJS. With Bun, it's about 2.5 times slower for this particular example. Deno and Node is about the same. So it's almost 6 times slower because it contains a way more things, way more APIs. So it naturally takes longer to start as well. All right. And if we take a look at how it would perform over a longer time, so this is a load test running a DynamoDB put, the same demo, actually the same code that we saw before, using ARM on 128 megabytes of memory configured, over 32,000 invocations. And here are the numbers. We can see here P99. This means that 99% of all invocations are below this number. So the first column is warm start, or I should say the first row is warm start and the second row is cold start. So we can see here for P99, we have 34 milliseconds for warm start and we have 84 milliseconds for cold start. And the fastest possible times that we can have, P0, so no times are faster than this. This is the fastest recorded time. We had 48 versus 5, so 5 millisecond warm start, 48 cold start. In comparison, this is Node.js 18. 20 has similar performance characteristics. There's not really a big difference, maybe slightly faster. But you can see here it's quite a dramatic difference. So for a warm start, we saw now we have a P99 of 164 milliseconds, and for a cold start, 1,306. Again, this is running the same code. And we have also 1,100 for cold start and around 5.85 for a warm start at the fastest possible time. So there's a 23 times performance improvement for the fastest times and a 15 times performance improvement for the slowest times for cold starts. And notice here also that the number of cold starts that occur when I run 32,000 invocations is that we only get 109 for LLRT and 554 for Node. So it's 5 times likely to hit the cold start. And this is because since the cold starts are so fast, it's very unlikely that we will hit another one, even running a load test. So it takes a while for Node to actually provision as many execution environments, since it's busy already serving one, right? So there's way more cold starts. So as soon as Lambda is already working on processing a request, if another one comes in, processing an event, I should say, another one comes in, we have to spawn an additional execution environment. That's why we see so many here versus LLRT. I want to also highlight here the difference here in warm start time from the fastest to the slowest. There's like a difference that is almost 160 milliseconds, whereas LLRT is only 29. So it's a much more stable performance curve there. And this, again, the major reason for this is the lack of a just-in-time compiler, where it's a more predictable and more stable, since we don't have to de-optimize and optimize code running on the fly. And what does this mean? So taking a look at the cost and latency for that particular test, we can see here that, that Node.js, it had a highlighter here. It had a build duration of 22 minutes and 19 seconds, and LLRT had only 7 minutes and 48 seconds. The total the duration here is a bit different between Node and JS, depending on how billing is calculated. But this means that we have a cost saving of 2.9x, and we're running the same code with LLRT, and a time saving of 3.7x, so 3.7 times faster in general across both cold starts and warm starts. And this project has received a lot of attention recently. So it's it has increased in popularity since its launch in February. In comparison here, we can see on star history that this is LLRT in red here, and we have SAM, which has steadily been increasing here since, I think, 2016 or something like that. And now we have LLRT playing catch up. So a lot of people have been starting this project. Doesn't mean that it's adopted, but there's a clear interest, and which makes me very happy and very excited as well. So that's pretty much it. This went a bit faster and smoother than I anticipated, so I think there's some room for Q&A. I didn't address roadmap, so maybe we can talk slightly about that as well, like what is happening. We're trying to reach what we call winter CG compliance, and winter CG is a working group that is trying to consolidate a minimal set of APIs between different JavaScript runtimes. So you can basically pick and choose whatever works best for you. So this is what we're trying to reach for the 1.0 release. Hopefully this will happen this year. Depends a bit on resources that we can allocate. But I'm hopeful. And when we reach winter CG compliance, we will be something closer to a 1.0 release. It's still very stable. So QuickJS is actually used in multiple projects. I think even Minecraft uses QuickJS in one form, and it's being used in, I think, in everything from databases to products from Microsoft as well. I'm not quite sure though, but I've seen it pop up here and there, which is very cool to see. So the engine itself is very stable, and LLRT is also quite stable. So if you encounter any bugs, the best thing you can do is to add a ticket. If something doesn't behave as expected, add a ticket on the repository. I think we can share a link to the repository here in the chat as well, or can you bring it up in the live stream maybe, James?
Yeah, we can do that. Yeah, we'll find a way to do that magic.
Yeah, exactly. Yeah.
Cool. On that point about roadmap, actually, one of the questions, it's quite a nice segue. One of the questions that Alan asked in the chat was, when can we expect LLRT to be natively supported as a Lambda runtime?
Yeah, that's a good question, and the answer is I don't know. I don't know yet, because it depends on a lot of things. We have to have a support structure. We have to have SLAs. It naturally has to reach more mature states in its API footprint. There's a couple of things that we haven't decided on yet. So hopefully it will be. But there are no guarantees what will happen. So right now it's I maybe mentioned this before, but it's an experimental product. So it's not an official AWS supported service or product, anything like that. It's more of a experimental way for us to try to make serverless extremely low latency and a runtime with extremely low latency.
Yeah, I mean, what some of the comments in the chat, some of the other comments are whether having a Rust as a managed runtime could be would that be a requirement, I suppose, for LLRT to be a managed runtime, would you say? Or is there not really a dependency there?
No, it's not really a dependency, since this is, the LLRT runtime, it's just a binary, so it doesn't depend on Rust more than at its compilation stage, right? So it might be something else. It might as well be C. So Rust has, it's what built it, but what comes out, there's no way to make, or like it doesn't have any dependency on Rust per se.
Okay.
And the tricky part of having compiled languages as provided runtimes in a general sense is that you're responsible for shipping what we call the runtime interface client, since it has to be part of your code. If you compare this with Node, for example, we at AWS can build what communicates with Lambda API and make sure that that works according to SLAs and according to best practices. It doesn't have any bugs or security vulnerabilities, etc. But in this case, you would have to be responsible for that. So that creates a bit of a complicated situation. Like, who's responsible? What if you don't patch or download the latest version of that runtime communication code, right? Are we responsible or are you responsible? And that creates a bit of a complication in comparison with other runtimes.
Yeah. Awesome. One final question for me that I was just thinking as you were talking through this. So some of the obviously I do a lot of stuff in the .NET world, and one of the things you can do in the .NET world for performance is native compilation. So you can compile things to a native binary and then run that on custom runtimes. And one of the things I've seen in some cases is, although your overall latency gets longer, your build duration goes up, as in, because you're now running on a custom runtime and not a managed runtime. Is that something you've seen with, like, how does this compare from like a cost perspective? Have you done any analysis on that, I suppose? Because using a custom runtime, you pay for more, right?
Yeah, and this is actually quite funny that you mentioned. So if you look at the pricing on Lambda, it actually says that you're being charged for everything, including the initialization. It's not just applied yet. So there's like no guarantees that says that init will be free. It is like that now. And to your point, now with a custom runtime, you're being charged for it, but with provided one, you're not right now. But the price, we haven't documented that it's for free, right? So it's something that people obviously are discovered. So I don't think you should depend on it. And for compile approaches like using Rust or something else, it's definitely worth it. It's worth to have that initial extra in iteration that you're being charged for, because it's so much faster overall. So you're paying maybe 40. Come again?
I was going to say, some of the numbers you put on there was like a third of the cold starts, right? With
exactly, yeah. Even at the in iteration, right? I think we saw something like 360 ms if memory serves me right? And I got in LLRT, I got something like 40. Right, so it's not, if it doesn't matter if it costs, right? And then you have the majority of the build duration there on the node was 960 or something, right? So it doesn't matter if I combine, because it's way much faster. That's why we saw the cost versus time saving, right? In the demo.
Awesome. Well, I will say a huge thank you. You've suitably blown my mind on lunchtime about all things Node and internals of how all this works. So I really, really appreciate you coming on, as do all of us in the Believing Service community. Definitely appreciate this, Richard. Any final comments? Anywhere, places people can reach you if they want to reach out and ask you questions?
I have a Twitter account, but I'm not there, or X, you should say now, or whatever. But I should definitely come hang out more in the Discord, in the Believing Serverless. And I have an account. I'll make sure to give a shout out in the channel, and you can come, chat with me. I would love to discuss serverless and optimizations and Rust and whatever floats your boat. I love this stuff. It really excites me. So I think that's the best way. And also you can reach me out on connect with me on LinkedIn and just chat. I think I also left my email in the slide deck as well. So you can just send me an email or whatever, just do a shout out, and I'm happy to talk optimizations or talk Lambda or Rust or serverless in general with anyone. I would love to do that.
Awesome. Thank you again, Richard. Really appreciate that. And I'll see you all, everyone listening later today, for Andrew's building some really cool stuff with Memento.
Yeah, and I think so. And finally, Elliot, Come here.
Of course, the dog.
Yes,
How
come.
did we forget the dog?
Yes, he's here. He's here.
Sorry, everyone.
Keep me company, but he's sleepy. He's sleepy. He will come.
If nobody saw this on LinkedIn, when I shared this on LinkedIn, there was talk about Richard's dog, and we had to see the dog. So there we go. The dog made it. Excellent. No, you could have done the whole thing with the dog on.
Yeah, he's so sleepy, right? Hello. He may be a bit annoyed now that I woke him up just to.
Oh, it's worth it. It's fine.
Yeah, it's worth it. Yes. All right.
Awesome.
Thanks, James. Thanks for having me.
Thanks.
Take care. See you. Bye.